Okay, so let's talk about a couple issues related to sequential design. Does it matter how we make state assignments? Well, from one perspective, no. Any assignment will work and we can get the same function. But from another perspective, yes, the state assignment could affect the circuit complexity. So for example, from our design above for the 101 recognizer, we used the following state assignment. But you could try out another one, for example, something like this, and you may actually get a simpler circuit. Okay, and then another question you may have is about the don't care states. Does it matter how I use them? Are they really don't cares? So first question would be, how could we ever get into a don't care state? And there's actually two ways this could happen. It could either happen on startup, or it may also happen because of an error that I can get into one of these don't care states. So can we get stuck in a don't care state? Well, sometimes. And is this a problem? Well, maybe. Depends on the application. So as an example, let's look at the don't care state for our sequence recognizer. So the unused state is 1, 0, and I'm going to call this D. So when I'm in state D, if I look at on my K-maps, the circuit that I built, what happens when I'm in state 1, 0, state D, and my input's a 0? So this is the bottom left box of my K-maps. In both cases, they were 0, so my next state's actually going to be 0, 0, or A. And my output, because my input's a 0, is also 0. What if I'm in state 1, 0, this unused state, and my input's a 1? So looking at my K-maps again, I would have 0, 1, which would be state B. And my output in this case would be a 1. So what does this mean? Well, if I ever had an error, and for whatever reason I end up in this state D, the good news is that at least after one clock cycle, no matter what the input is, I'm going to end up back in my original state diagram or operating the right FSM. For some circuits though, and some sequential implementations, you might have your don't care states with no path or no connection back to the original state diagram, the finite state machine, and instead they might have a cycle in themselves. So depending on the application, this could be bad. If I get stuck if I have an error and I get into one of these states, I'm going to be stuck not operating the right sequence. So for this reason, we sometimes make sure that there is at least one path from our don't care states back into the right state diagram so that the circuit could eventually recover. And this is sometimes called a self-starting circuit. Okay, so let's talk about one more issue with designing an FSM. So for this particular design, we chose to use a Mealy style, but I could have also used a Moore style. And for any FSM or sequential circuit, you can build it either way. And in fact, you could also convert between the two. So for example, if I wanted to change this to a Moore implementation, I would do something like this. So this is my original Mealy state diagram. And so to create the Moore from the state diagram, I'm going to look at all the states and specifically the incoming edges to each state and see the states where there are edges with different outputs. The states that have the same outputs coming into them, I'm going to go ahead and associate that output with that state. So for example, A has two edges coming into it and the output is 0 in both cases. So for my Moore FSM, I'm going to have a state A and the output will always be 0 when I'm in state A. This will also be my start state. Same thing for state C. There's only one edge coming in and it's 0. So C will always output a 0. But for B, if I look at it, depends on where I'm coming from and what the input is. So for these two edges, the output's a 0, but for the edge coming from C, if the input's a 1, then the output's a 1. So I'm going to split this into two states, call it B0 and B1, where the output for B0 is 0 and the output for B1 is 1. Okay, now that I've split the states, let's go ahead and fill in the edges. So if I'm in state A and the input's a 0, I stay in state A. If it's a 1, then I want to go to state B, but the output's a 0, so I'm going to go to B0. From state C, if I have a 0, I go to A. And if it's a 1, I go to B, where my output's a 1, so I'm going to go to B1. Now, from state B0, if my input is a 1, then I'm going to stay in state B, my output's a 0. And if it's a 0, then I'm going to state C. From B1, if my input's a 1, then I'm staying in B and the output's a 0. So in my more finite state machine, that means I'm going to transition to the state B0 where the output's 0. And if I have a 0, then I go to state C again. Okay, and so now I have a more finite state machine for implementing the same circuit. Now, let's look at the timing diagram though, because it will be slightly different. Okay, so this was the timing diagram we filled out earlier for the Mealy finite state machine on the left. The input sequence is still the same for my more on the right, but let's fill out what the states are, the state transitions. So I start off in state A, then I read in a 1, so I'm going to go to state B0, and then I read a 0, so I go to state C, and then I get a 1, so then I'm going to go to state B1. In B1, I get another 1, so I go to B0. Then I get another 1, so I stay in B0. Then I get a 0, so I go back to C. Then I get another C, so I go to A. Another 0, and I stay in A. Okay, so let's look at the more output now. So for the more finite state machine, the output, by definition, only depends on the current state. That's why we've gone ahead and included the output inside the bubbles below our state symbol. So the output is only a 1 when I'm in this state B1. The output will be 0 until I get to state B1. Now, as soon as I go on this clock pulse into state B1, the output's also going to go high, and will stay high that whole clock period when I'm in state B1. Then it's going to go low again because I transition between these other states where the output's a 0. Okay, so notice that the output looks slightly different for the more FSM versus the Mealy FSM. But when I interpret the results of that output, actually they're telling me the same thing. After the first 3 clock pulses, I'm seeing that I've recognized my sequence, and then I don't recognize it again. Now, you may notice that for the more finite state machine, it's a little bit easier to interpret because the output is synchronous. It only changes on the clock edges because it just depends on the state, which is also synchronous. So I don't have this momentary transition as I did with the Mealy finite state machine, shown down here. So this is an advantage for designing an output using the Moore style. The disadvantage of a Moore versus Mealy, as we can tell above, is that I tend to have more states with a Moore style output than using a Mealy style output. But that said, it's typically not many states, and so it really depends on the application and the context, which style you use, but both of them can be used for any application.